Imagine standing beside one of the giant engines used to propel an ocean-going cargo ship. The cylinders tower above the crew. Inside the engine, massive pistons, connecting rods, and a crankshaft are built to move a ship weighing tens of thousands of tons across entire oceans. Now compare that with a car. You turn a key or press a button. A compact electric starter rotates the engine until combustion takes over. So why not scale that system up? Why not build an enormous electric starter for an enormous ship engine? For the large low-speed engines used on many major cargo ships, the solution is not simply a larger version of the system in a car. The starter would have to overcome the resistance of enormous internal components and begin rotating the connected machinery from a complete standstill. Instead, the first rotation comes from a completely different source. Before that source can be used, however, the engine must be prepared. Starting one of these engines does not begin when the crankshaft turns. It begins while the machinery is still motionless. One of the first requirements is lubrication. Oil is circulated through the engine before the heavy internal parts begin moving. It reaches bearings and other surfaces that will soon carry enormous loads. That oil creates a protective film between moving metal surfaces before the first rotation begins. The engine must also be in the proper thermal condition. A recently stopped engine may still be warm and relatively close to its operating condition. An engine that has remained shut down for much longer may need additional preparation before it can be started safely. On large, low-speed marine engines, the jacket water system can be used to maintain or restore the required temperature before startup. At this point, pumps may be running, oil may be circulating, and temperature may be under control. Yet the engine itself has still not moved. Preparation protects the machinery. It does not create the first rotation. Something still has to push the pistons. That first push does not come from fuel. It comes from compressed air. Before the engine is started, compressors fill large pressure vessels known as starting air receivers. The air inside them stores energy until the starting sequence begins. When the crew gives the start command, the stored air is released through large pipes toward the engine. On many large low-speed marine engines, that air provides the force needed to begin turning the crankshaft. This is fundamentally different from the way a car starts. A car uses an external electric motor to rotate its engine. Here, stored air is sent into the engine itself. That is the first major answer to the title question. The engine's first movement is created before combustion begins. It starts with energy stored in compressed air. If you enjoy seeing how enormous machines solve problems that ordinary machines never face, subscribe to the channel. Now the remaining question is where that air actually acts. The answer is inside the cylinders. On the large low-speed engines examined here, each cylinder is equipped with a starting air valve. At the correct moment, the valve opens and admits high-pressure air into the cylinder. The air acts directly on the piston. As the piston moves, the connecting rod transfers that force to the crankshaft. This creates the engine's first controlled movement. The compressed air is not turning the machinery through a separate motor mounted outside the engine. It acts in the same cylinder where combustion will soon produce power. That direct action is what allows the system to move such massive internal components without relying on one enormous external starter motor. One push, however, is not enough. If only one cylinder received air once, the crankshaft would not continue rotating smoothly. Several cylinders must contribute in sequence. The engine does not admit starting air into every cylinder at the same time. It delivers the air in a controlled sequence. As the crankshaft changes position, the appropriate starting air valve opens. One piston adds a push. Then another cylinder takes over. The key is not pressure alone. It is timing. Each burst of air must act when the piston can continue driving the crankshaft in the required direction. The process builds rotation step by step. One cylinder moves the crankshaft forward. The next maintains the motion. Another continues the sequence until the engine is turning steadily enough for the next stage. On reversible low-speed engines that directly drive the propeller, the starting sequence can also be arranged for the required direction of rotation. By now, compressed air has solved the original problem. The engine is no longer stationary. The pistons are moving, the crankshaft is turning, and the engine is approaching the condition needed for combustion. The air has created motion. Now, fuel must make that motion self-sustaining. As the crankshaft turns, the engine reaches the point where fuel can be introduced. Fuel is injected into the hot, compressed air inside the cylinder. It ignites, and the expanding gases drive the piston downward. The engine now begins transitioning from stored starting air to combustion. The same pistons that were first moved by compressed air are now driven by burning fuel. Once combustion becomes stable, starting air is no longer needed. The starting air valves close, and the engine continues under its own power. This is the handover the entire system was designed to achieve. Compressed air creates the first rotations. Combustion keeps the engine running. Starting air is therefore not a fuel, and it does not propel the ship during normal operation. Its role is brief but essential. It gives the engine enough controlled movement for normal combustion to begin. Once the engine is running, it no longer needs the starting air supply, until another start is required. That next start, however, may happen under very different conditions. A restart after a brief shutdown and a start after a long period at rest are not the same operation. If the engine has only been stopped for a short time, much of its structure may still be warm. Its support systems can often return it to a ready condition more quickly. After a long shutdown, the engine may have cooled substantially. The preparation systems must then restore the conditions needed for a safe start. Oil must be circulating before movement begins. Temperature must be managed. The starting air system must also be available and pressurized. Only then can compressed air begin turning the engine. This is why simple claims that a giant ship engine either starts instantly or always takes hours are misleading. The actual preparation depends on the engine, its installation, how recently it was operating, and how long it has been shut down. Compressed air creates the visible first movement, but the success of that start depends on everything completed before the air valves open. Starting the engine is not one action, it is a coordinated sequence. At the beginning, the problem looked like one of brute force. How do you turn machinery this large from a complete standstill? The answer is not one gigantic starter motor. It is a series of systems, each solving one part of the problem. Lubrication protects the machinery before it moves. Thermal preparation brings the engine into the right condition. Compressed air enters the cylinders and creates the first rotations. Precisely timed starting air valves keep the crankshaft moving. Then combustion takes over and allows the engine to run on its own. No single component performs the entire task. The process works because each system acts at the correct stage and then hands control to the next. That is what it takes to start a giant ship engine. Not simply more power, but preparation, stored energy, precise timing, and a controlled transition to combustion. The first movement of the crankshaft may happen quickly. The engineering that makes it possible begins long before anything moves.